host.
හරි රෙකෝඩ් වෙන්න පටන් ගත්තා.
හරිද රෙකෝඩ් වෙනවා? Okay, so I'll start where we stopped. So I was talking about how to implementing that. How to find those coefficients using in a hardware setup, right? So there are two methods. So the first method is to use that equation that we got. So in that equation we have Ci equal to integral xt phi it dt, right? So what we can do is, so if this is xt, our incoming signal, and we can multiply these signals with each of these basis functions, right? So we can do it with all these basis functions, all the n functions. Then we can send it through an integrator, right? So then from this we get C1, and if I send this through an integrator, this is C2. This is Cn, right? So this is one method. So here thing is that we need n number of multipliers and n number of integrators, right? So okay, so the next method is to use a filter, use filtering, right? So in the second method, so let me explain it this way. So if we have a filter, a linear time invariant system like this, suppose y t minus t, right? The transfer function is this impulse response. So the output of this is rt, right? So the output rt can be written as the convolution between these two, right? So if I expand this convolution, it will be x tau y t minus, so instead of t I have to plug in t minus tau, right? dt. So you know the definition of convolution, right? So this is like this. So this will be x tau y t minus simple t plus tau dt. So what we do is, this output we sample it when t time equals capital T, right? So if we sample this output, it will be x tau y t minus simple t plus tau dt, where t is equal to capital T, right? So what I have to do is, I have to plug capital T instead of simple t, so this will cancel out. So what we get is x tau y tau, so d, so these are d tau, right? Sorry for that, there's not dt, d tau, right? So this is d tau. So if we compare it with our result, so if this is our signal, and if yt is one of these basis functions, this will give the result that we want, right? So that means if we do an implementation like this, that means we have xt coming in, and we have linear time invariant system v1 capital T minus simple t, and we sample the output of that when simple t equals capital T. So this will actually give us this integral xt v1t dt, right? So this will be c1, right? So likewise we can have a number of such filters, uh, and sample the output and get each of these coefficients. This is Cn, right? So that is the second method. So, and there's another thing that we need to consider, that deciding this T, right? So you know that in a real communication system, we have to deal with, in my real real system, that means causal systems, right? So causal systems are the systems that we can realize. So in that case, this so let's say this filters transfer function. So if I take pt is something like this, say p1t is like this, right? So its duration is t naught in the time domain. So then if I write if I draw v1 minus t, it will be like this, from minus t naught to 0, and v1 capital T minus simple t is where this is shifted by an amount of capital T, right? So then this point will be capital T minus T naught. This will be capital T, right? So if this filter to be causal, there cannot be, so this cannot happen. That means there cannot be anything in the negative side, right? So that means T minus T naught should be greater than or equal to 0, right? So our T should be greater than or equal to T naught. So T, where T naught is the duration of this basis signal in the time domain, right? So actually this is of v1t, right? So there are n of them. So when we are deciding a T for this system, we have to get T naught of each one of these and take the maximum of that, and need to decide a capital T value which is greater than that maximum value, right? So that it will be matching for all of these, right? So to make all of these causal. Okay, right. Next one is how to find the set of minimum energy signals. So this is I have seen that there are questions from this upcoming section directly. So if I take the set of how to find set of minimum energy signals. So let's say we have a set of signals S1t, S2t, SMT, right? So I'm number of signals, and each of these have energies E1, E2 likewise EM, right? So this is the set of energies, right? So this is the set of signals, this is the set of energies. And also when we are transmitting these signals and also these energies, you know, we take the vector representation, we can write them like this, right? Likewise, that means the square norm of these vectors, right? And also when we are transmitting these signals, you know, so these signals can transmit, so there's a probability that each of these signals can occur, right? So that is called the priority probability. So this is the set of priority probabilities of the signals. Okay, so there are methods, there are several methods to find the energy. So one of them is to find the peak energy. So that means the maximum out of these set of energy, right? And the second method is to find the mean energy. So mean energy is 1 over m sigma ei, right? So that means we sum all these and take divided by the number of signals. So that is the mean energy. So out of this, what we are considering is the average energy. So average energy take these priority probabilities into consideration. So it can be written as Pi EI, right? So this is actually Pi times the square norm of these vectors. So this is actually the expected value, right? So expected value of this norm distribution, norm, right? So that's the average energy. So if these signals are equiprobable, so that means that all of these priority probabilities are equal. So in this case, then it will be Pi equals 1 over m for all I, right? So in that case, average energy and mean energy will be the same, right? Because priority probability will be 1 over m, so we can take that out. So we'll get the same as before, right? So what we need to know is when we are given a set of signals, how to find the set of uh, minimum energy signals, right? So let's say that we were given that previous set of signals and asked to find the set of minimum energy signals. So that means that we have to adjust our constellations in such a way that the energy of the signals are minimum, right? So it is desirable because that we don't want to spend much energy to transmit the same thing if we can do it with a lesser amount of energy, right? Okay, so what we are going to do is, let's suppose that there's another vector a, right? So this is a constant vector. That means it is something of some position in the space of the constellation, right? So if we take the energy of this set of signals, average energy, with respect to this point, so it's something like that the constellation is centered around this a, right? So that means not the origin, around a. So when we are considering the energy, what we take is the distance between a and each of these vectors, right? These signal vectors. So I can write the energy as Pi Si minus A norm square, right? I goes from 1 to m, right? Then we need to find this A such that E is minimum, right? So we need to minimize E with A, right? So we need to find the A which minimizes E, right? So let's see how we can do that. So can write E as a function of A. So it will be sigma Pi Si minus A norm squared. So I think you remember how we expand this. So this is in vector terms. So in vector terms, I can write this norm squared as the transpose of the vector multiplied by the vector, right? So this will give the square of norm, right? So then this will be Si transpose minus A transpose times Si minus A, right? So this is actually a dot product here. So if I expand this, this will be Pi times Si transpose Si plus A transpose times A, this term, and there will be a middle term, so which has Si transpose dot A minus A transpose dot Si. So these two are the same, right? So if we multiply A transpose with Si or Si transpose with A, it will give the same answer. So can write Pi. So this is actually the norm, squared norm of Si, and the next term will be square norm of A, and these two are the same, so I can write that as minus 2 times sigma Pi A transpose dot Si, right? So then I can further write this like so. I can take this A norm out because it's a constant. So what I get inside that is sigma Pi, and also I can take A transpose out of the third one. So here I will have sigma PISI, right? It's the dot product, right? Then EA will be, so I cannot do anything to this, so it will be the same. And here this sigma Pi is equal to 1 because, you know, when you add all the probabilities together, it should be 1. So that is 1. Then this is the norm, square norm of A, and minus this term, right? Twice sig A transpose sigma this. Okay. So when we so as we did earlier, we can write these two together in a as a let me write it's like this. So this will be sigma Pi Si norm squared. So this I can write A minus sigma Pi Si norm squared. So this will give this term this term